Problem number 18. An extendable arm is made from rigid beams free to pivot around the dots shown. Spring 1 with the equilibrium length L1 is attached between points A and C, while spring 2 with the equilibrium length L2 is attached between B and D. The system is allowed to come to equilibrium. In equilibrium, what is the ratio of the tension in spring 1 to the tension in spring 2? Solution for problem number 18. Let's write expression for full potential energy of this system. Suppose that first spring has a spring constant K1, second spring has a spring constant K2, and the distance in equilibrium position between neighbor points like B and C equal x. So it means that total potential energy will be this expression. To find where is the minimum for this potential energy, we need to take first derivative by x, and that will be this equation. Here we have L minus 3x, that's extension for the first spring, and L2 minus 2x, it's extension for the second spring from equilibrium, but K1 multiplied by extension, that's a tension in the first spring, and K2 multiplied by extension, that's a tension in the second spring. So finally we have 3T1 plus 2T2 equals 0, and T1 over T2 equal negative 2/3. That's answer A, and it was solution for problem number 18. Problem number 19. Consider an axially symmetric object that experiences no external forces and initially rotates about its symmetry axis. The object then changes its shape while remaining axially symmetric. Afterward, it is found that its moment of inertia about the symmetry axis has increased. How have its kinetic energy T and the angular velocity omega changed? Solution for problem number 19. Let's write expressions for angular momentum and kinetic energy. Angular momentum L equal moment of inertia multiplied by omega, and the angular momentum is conserved, means that L is constant, and if we will increase moment of inertia I, omega must decrease, and also kinetic energy equal 1/2 I omega square, or we can rewrite it in form of 1/2 L square over I. L is constant, so it means that if I is increased, kinetic energy decreased, and the total answer is A. T has decreased and omega has decreased. That was a solution for problem number 19. Problem number 20. A well-calibrated scale reads 0 when nothing is placed on it. When a deflated balloon is placed on the scale, it reads m small g. When a non-airtight box is placed on the scale, it reads big mg, where big M greater than small m. The balloon is inflated with helium so that it floats upward in air. The balloon is placed in the box, and the box is placed on the scale. If the scale reads W, which of the following is true? Solution for problem number 20. Consider the forces on the box. Before the balloon is in the box, the weight of the box, the buoyant force on the box due to the atmosphere, and the normal force from the scale all balance, and the normal forces big mg. When the balloon is placed in, the only change in the forces on the box is an upward force as the balloon pushes up on the top of the box. Thus, the answer must be less than big mg. However, we don't know whether it is larger or smaller than big M minus small m multiplied by g, because this depends on how buoyant the balloon is, so there is not enough information to decide. And this is answer E. None of the above are necessarily true. And that was solution for problem number 20. Problem number 21. A person stands on the seat of a swing and squats down, so that the distance between their center of mass, cm, and the swing's pivot is L. As the swing gets to the lowest point, the speed of their center of mass is v. At this moment they quickly stand up and thus decrease the distance from the center of mass to the swing's pivot to L prime. Immediately after they finish standing up, their center of mass speed is v prime. Which of the following statements is correct? You might neglect friction, the change in the moment of inertia of the person about their center of mass, and the time take to stand up. Solution for problem number 21. Because the person is doing work to stand up, the energy is not conserved in this problem. Instead, the angular momentum about the swing pivot is conserved, since there is no net torque. The angular momentum about the person's center of mass is mvl while squatting, and mv prime l prime after they stand up. The linear momentum is not conserved because the internal forces in the swing give the person an impulse as they stand up. And due to angular momentum conservation, we have this relation, and from here correct answer is C. VL equal V prime L prime. That was a solution for problem number 21.